March 19th, 1943. Wright Field, Dayton, Ohio. The temperature inside the experimental gunnery range had dropped to -40°F, simulating conditions at 30,000 feet. Major General Oliver Echols stood behind a plexiglass observation window, watching a test that would determine whether the Army Air Corps' most expensive weapons program would succeed or fail. On the firing line, a mock-up of the Sperry Central Station computer system sat connected to a hydraulic gun turret. The periscope sight, manufactured by Eastman Kodak's Hawkeye works, protruded from the gunner's station like a submarine's conning tower. The entire assembly had cost $3.2 million to develop, and in 60 seconds, it was about to prove catastrophically inadequate. The test gunner tracked a simulated enemy fighter moving at 400 miles per hour. He centered the reticle, matched the diamonds to the target's wingspan, and squeezed the trigger. The computer hummed. The turret tracked smoothly. The guns fired. Every round missed. The gunner tried again. Another miss. The periscope's complex optics had frozen solid in the cold. The image flipped inverted as the sight tracked below the horizontal plane, disorienting the gunner. The hydraulic system, pressurized to 5,000 pounds per square inch, leaked fluid that congealed in the sub-zero temperatures. General Echols watched the demonstration for another 5 minutes, then walked to the observation room's telephone. The call he placed would redirect $3 billion, mobilize an engineering team of over 2,000 people, and ultimately create the world's first mass-produced electronic computer system. The problem facing Echols wasn't just technical, it was existential. The B-29 superfortress represented America's answer to the strategic challenge of the Pacific War. Japan's empire stretched across 6,000 miles of ocean. To bomb the Japanese home islands, American bombers would need to fly from distant island bases, crossing vast stretches of water with no possibility of fighter escort for most of the journey. The bomber would have to defend itself. Traditional defensive arrangements, proven inadequate in European skies, would be suicide over the Pacific. German fighters had learned to attack B-17s from head-on, exploiting the limited forward firepower. They had developed rocket-propelled weapons that allowed them to engage from beyond the effective range of 50-caliber machine guns. American bomber losses over Germany averaged 6% per mission. At that attrition rate, aircrew had a 25% chance of completing a 25-mission tour. The mathematics were brutal and undeniable. The B-29 needed something revolutionary, not incrementally better, fundamentally different. Boeing's engineers had already pushed boundaries that seemed impossible. They had designed a pressurized fuselage that could maintain cabin pressure at 30,000 feet, where the outside air temperature reached -60 degrees. They had incorporated tricycle landing gear, a radical departure from the tail-dragger configuration every other bomber used. They had specified 4 Wright R-350 duplex Cyclone engines, each producing 2,200 horsepower, making the superfortress the most powerful aircraft in existence. But all that engineering brilliance meant nothing if the bomber couldn't defend itself. The Army Air Corps had issued requirements for the Central Fire Control System in January 1940. 4 companies responded to the request for proposals: Bendix, General Electric, Sperry, and Westinghouse. Each promised to deliver a system that would allow gunners seated in pressurized compartments to control remote turrets mounted throughout the aircraft. The specifications were daunting. The system needed to compensate for aircraft speed, gravity, temperature, humidity, parallax between sight and guns, bullet trajectory, and target deflection. It needed to do these calculations in real time, faster than any human could compute. It needed to be reliable at altitudes and temperatures that would freeze hydraulic fluid and shatter optical glass. And it needed to fit inside an aircraft that was already pushing weight limits. In April 1940, Sperry Gyroscope Company won the primary contract. The decision made sense on paper. Sperry had been developing fire control systems since World War I, when their equipment directed naval guns on battleships and cruisers. By 1940, Sperry fire control computers guided anti-aircraft batteries protecting American cities. Their engineers understood ballistics, understood lead computation, understood the mathematics of intercepting moving targets. The company had pedigree, experience, and a track record of delivery. The Army Air Corps brass believed Sperry would deliver the impossible, because Sperry had delivered the improbable before. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But General Echols hadn't survived 2 decades in military aviation by trusting single sources. He insisted on a backup contract. General Electric received authorization to develop their own fire control system in parallel, a hedge against Sperry's potential failure. The GE contract was smaller, the timeline more compressed, the expectations lower. It was insurance, not preference. GE had built the first general-purpose electromechanical computer at MIT between 1928 and 1931, based on Vannevar Bush's differential analyzer design. They understood analog computation, but they had never built fire control systems for aircraft. They were the underdog, the backup plan, the team nobody expected to win. The Sperry system was elegant in concept. Periscopes would project up and down from the gunners' stations, allowing them to sight enemy aircraft while remaining in pressurized comfort. The periscopes connected to hydraulically operated turrets that could retract into the aircraft's fuselage, reducing drag when not in use. The entire system embodied sophisticated engineering. Eastman Kodak's optical engineers in Rochester had designed periscope optics that could track targets through 360 degrees of rotation. Sperry's mechanical engineers had created hydraulic actuators capable of moving turrets weighing hundreds of pounds with precision measured in fractions of a degree. On the drawing board, the system was revolutionary. In the freezing cold of the Wright Field test range, it was a disaster. The periscope optics that worked flawlessly in Kodak's heated laboratories froze at operational altitude. The complex lens arrangements, designed to provide crystal-clear images, fogged with condensation as warm air from the pressurized cabin, met sub-zero temperatures in the periscope tube. The hydraulic fluid that moved turrets smoothly at sea level turned to sludge at -40 degrees. Seals leaked, pumps cavitated. The retractable turrets, so aerodynamically efficient, created mechanical complexity that multiplied failure modes. Every advantage on paper became a liability in practice. General Echols had seen enough. In March 1943, with B-29 production already underway, with factories in Wichita and Renton building aircraft that couldn't defend themselves, with billions of dollars committed and the Pacific War intensifying, he made the call. Sperry was out. General Electric was in. The backup plan became the main effort. And GE had approximately 6 months to deliver a working system before the first B-29s rolled off production lines. The GE engineering team, led by a cadre of electrical engineers who had cut their teeth on power distribution systems and industrial controls, approached the problem differently. They abandoned hydraulics entirely. The turrets would be electrically powered, driven by Amplidine motor generators that could deliver massive torque through compact, lightweight systems. They abandoned retractable turrets. The weapons would remain deployed, mounted in fixed positions on the aircraft's hull, reducing mechanical complexity but increasing drag. Most importantly, they abandoned periscopes. Gunners would sight through simple reflector gun sights mounted in plexiglass blisters. What they lost in optical magnification, they gained in reliability. The heart of the GE system was the analog computer, not a single computer, but 5 separate units, each dedicated to a specific gun turret. Each computer weighed approximately 150 pounds and measured roughly 6 feet long, 3 feet wide, and 3 feet tall. Inside that box, hundreds of relays, cell sins, amplifiers, and resistors formed an electromechanical brain that could solve differential equations faster than any human mathematician. The computer received inputs from the gun sight, from airspeed indicators, from temperature sensors, from altitude gauges. It calculated bullet trajectory, accounting for the fact that a .50 caliber round fired at 30,000 feet would follow a different path than the same round fired at sea level. It computed lead, determining where a fighter traveling at 450 miles per hour would be by the time bullets traveling at 2,900 feet per second reached the intercept point. It compensated for parallax, adjusting for the offset between where the gunner aimed and where the guns actually pointed. And it did all of this in fractions of a second, continuously, tracking targets that could change direction, speed, and altitude in the blink of an eye. The system worked through a network of cell SINs, electrical position indicators that compared the line of sight with the line of fire. When the gunner moved his gun sight to track a target, the cell SINs at the sight and the cell SINs at the turret measured any difference between where the sight pointed and where the guns pointed. If a difference existed, an electrical signal representing that error fed into a servo amplifier. The amplifier boosted the signal and sent it to an Amplidyne motor generator. The Amplidyne generated voltage that drove the turret motors, moving the guns until the cell SINs reported that sight and fire aligned. The entire feedback loop operated continuously, making hundreds of tiny corrections per second, keeping the guns trained on target as both bomber and fighter maneuvered through three-dimensional space. But the real innovation wasn't the hardware, it was the architecture. The GE system didn't just control turrets, it networked them. Each of the 5 sighting stations, located in the nose, tail, and 3 plexiglass blisters on the central fuselage, could control multiple turrets through a system of electrical switches. If a fighter attacked from directly ahead, the bombardier in the nose station could simultaneously operate both the upper forward turret and the lower forward turret, concentrating 8 50 caliber machine guns on a single target. If fighters attacked from the side, the gunners in the blister stations could coordinate fire from multiple turrets, creating overlapping fields of fire that no attacker could evade. The upper gunner, positioned in the aircraft's dorsal blister, acted as fire control officer, coordinating the distribution of turrets among all gunners during combat, shifting firepower to meet threats as they developed. This capability, to concentrate multiple turrets on a single target, transformed defensive gunnery from individual weapons to integrated systems. A B-17 Flying Fortress carried 13 50 caliber machine guns, but each gunner fought his own private battle, unable to coordinate fire with other positions. A-29 carried only 12 guns, one fewer than a Fortress, but through the central fire control system, 6 or 8 guns could converge on a single attacker. The mathematics were unforgiving. A Japanese fighter approaching head-on faced not 2 or 3 guns, but potentially 8, all computer-aimed, all firing in coordinated bursts. The difference between scattered harassment and concentrated destruction. Development proceeded at breakneck pace. GE's engineering facilities in Schenectady, New York, ran 3 shifts, 7 days a week. Machinists fabricated custom turret housings. Electricians hand-wired computer units, soldering thousands of connections following schematics that changed weekly as engineers refined the design. Test pilots flew modified B-29s with prototype systems installed, pushing the aircraft to operational limits, deliberately inviting system failures so engineers could identify and eliminate problems before production. The failures were numerous and instructive. Early turret motors overheated, burning out after sustained firing. Engineers redesigned the cooling systems, adding ventilation that directed the slipstream through the motor housings. The electrical load from 5 turrets operating simultaneously overwhelmed the aircraft's power generation capacity. Boeing modified the B-29's electrical system, adding generators and upgrading distribution buses to handle peak loads that exceeded 100 kilowatts. The gun sights fogged in humid conditions. Engineers added heating elements that kept the glass clear even when outside temperatures dropped below -50 degrees. Each failure prompted redesign. Each redesign was tested. Each test revealed new problems. The cycle repeated endlessly, consuming months and millions of dollars. By summer 1943, the system was working, not perfectly, but adequately. Gunners at the Wright Field test range in Florida were achieving hit rates that astounded observers accustomed to conventional defensive armament. Against towed targets moving at 300 miles per hour, gunners scored hits on 20 to 30% of their aimed shots. Against slower targets, the hit rate climbed above 50%. The effective range of the system, the distance at which a gunner could reasonably expect to hit a target, extended to 900 yards, 50% beyond the 600-yard effective range of manually aimed guns on B-17s and B-24s. The difference wasn't incremental, it was revolutionary. The mathematics of aerial combat are unforgiving. Effective range determines engagement duration. A fighter attacking a B-17 would enter the bomber's defensive envelope at 600 yards and could continue pressing the attack until reaching minimum safe separation, perhaps 100 yards. That gave the fighter roughly 3 seconds of invulnerability beyond the bomber's guns, followed by approximately 8 seconds within effective defensive range. Against a B-29, that same fighter entered the defensive envelope at 900 yards. The bomber's gunners had an additional 3 seconds to track, aim, and fire. In aerial combat, where closure rates approached the speed of sound, 3 seconds meant the difference between a near miss and a killing burst. But the real advantage emerged when multiple turrets engaged simultaneously. Conventional bombers relied on formation flying to create overlapping fields of fire between aircraft. A combat box of 18 B-17s would position aircraft so that gaps in one bomber's defensive coverage were filled by guns from neighboring aircraft. It worked, but it required rigid formation discipline. Aircraft had to maintain precise spacing even during bomb runs, even when under attack, even when engines were failing and control surfaces were shot away. The formation was only as strong as its weakest link. One bomber falling out of position created a gap that experienced fighter pilots exploited, ruthlessly. The B-29, with its networked fire control, created overlapping fields of fire within a single aircraft. Multiple turrets could engage a single target, concentrating fire that made evasion nearly impossible. Formation flying remained important, but individual aircraft possessed defensive capability that made them less dependent on mutual support. General Curtis LeMay, commanding the 21st Bomber Command, recognized this capability immediately. His B-29s would fly missions that B-17s could never attempt, long-range strikes with minimal fighter escort, relying on altitude, speed, and revolutionary defensive armament to survive. June 5, 1944, Chengdu, China. The first operational B-29 superfortresses of the 20th Bomber Command sat on newly constructed airstrips carved from rice paddies. Each aircraft represented the culmination of $3 billion in development, thousands of engineers working around the clock, and a gamble that computer-controlled defensive armament would work in combat. The crews preparing for the first mission against Japanese targets had trained on the GE Central Fire Control System for only 6 weeks. Most had never fired the guns in anger. In approximately 8 hours, they would face the Imperial Japanese Army Air Force over Bangkok, and the entire B-29 program would be validated or exposed as a catastrophically expensive failure. Staff Sergeant Kenneth Idness settled into the upper gunner's position of his assigned superfortress. At 23 years old, the former farm boy from North Dakota had qualified as a central fire control gunner, the position responsible for coordinating defensive fire among all turrets during combat. His station, mounted in a plexiglass blister that protruded from the aircraft's dorsal surface, provided 360 degrees of visibility. In front of him, the reflector gun sight displayed a reticle of dots arranged in a circle around a center point. To his left, a control panel bristled with switches that allowed him to transfer turret control between gunners. Behind him, electrical cables snaked through the pressurized fuselage, connecting his station to the 5 analog computers distributed throughout the aircraft. Idness had spent the previous 6 weeks learning to trust the system. The concept violated every instinct developed during gunnery training. Traditional defensive gunnery required the gunner to estimate range, calculate lead, compensate for bullet drop, and adjust for his own aircraft's motion, all while a fighter closed at combined speeds approaching 600 miles per hour. They fired instinctively, hosing streams of tracers toward attackers and hoping a few rounds would connect. The hit rates reflected this reality. Against maneuvering targets, conventional gunners scored hits on perhaps 5 to 10% of their fired rounds. The rest disappeared into empty sky, wasted ammunition that added weight without providing defense. The GE system demanded a different approach. The gunner's only job was to track the target smoothly, keeping the reticle centered on the enemy aircraft. The computer handled everything else. It measured the angular rate at which the target moved across the gunner's field of view. It calculated range by comparing the target's wingspan to the spacing of the reticle diamonds. It determined the target's velocity vector, predicting where the aircraft would be when bullets arrived. It compensated for gravity, for air density, for temperature, for the parallax offset between sight and guns. The gunner simply tracked and fired. The computer did the thinking. During training, Eidness had been skeptical. The system seemed too complex, too dependent on technology that could fail. But on the test range at Pratt Army Airfield in Kansas, he had watched his tracers converge on towed targets at distances that would have been impossible with manual sighting. The computer worked. The question was whether it would continue working when Japanese fighters came screaming out of the sun with 20mm cannons blazing. The mission to Bangkok launched at 1400 hours local time. 98 B-29s, the largest force of superfortresses yet assembled, formed up over China and turned southwest toward Thailand. The target was the Makassan Railway Yards, a logistics hub supporting Japanese operations in Burma. Intelligence predicted heavy fighter opposition. The Imperial Japanese Army Air Force based approximately 80 fighters at Don Muang Airfield near Bangkok, including Nakajima Ki-43 Hayabusa fighters and Kawasaki Ki-45 Toryu twin-engine interceptors. Japanese pilots had been studying B-29 operations since the bombers began staging through China in April. They understood the superfortress flew higher and faster than B-17s or B-24s. They were developing tactics specifically designed to counter the new threat. The bomber stream crossed into Thailand at 26,000 feet, above the effective ceiling of most Japanese fighters, but within range of the newer models. At 15:45 hours, radar operators detected the first enemy aircraft climbing to intercept. Within minutes, dozens of fighters swarmed the formation. The engagement that followed would provide the first combat test of technology that had consumed 3 years of development and hundreds of millions of dollars. Eidness spotted the first attacker at approximately 3,000 yards, a single-engine fighter climbing steeply toward the formation's high element. He centered the reticle on the aircraft, adjusted the diamond spacing to match the fighter's wingspan, and began tracking. The GE computer hummed to life. Celsins measured the sight's position. The analog circuits calculated intercept solutions. The upper forward turret, controlled from Eidness's station, began tracking the target independently, the guns moving to aim at a point in space where the computer predicted the fighter would be when bullets arrived. The fighter closed to 1,200 yards. Eidness could see the distinct lines of a Ki-43, its fixed landing gear and radial engine unmistakable. The Japanese pilot was experienced, approaching from a steep angle that would have defeated conventional defensive fire. Against a B-17, he would have been outside effective range until closing to 600 yards or less. Against the B-29's computer-aimed system, he had been within the engagement envelope for nearly 10 seconds. Eidness squeezed the trigger. The upper forward turret erupted, 4 50-caliber machine guns firing in coordinated bursts. The computer continuously adjusted aim as the fighter maneuvered, keeping the guns trained on the projected intercept point. Tracers arced toward the target, the stream bending through space as gravity and air resistance affected the bullet's trajectory. The fighter pilot, likely expecting defensive fire to begin at much closer range, continued his attack run for 2 more seconds. Then the computer-aimed rounds found their mark. The first hits sparkled along the Ki-43's wing route. The 50-caliber armor-piercing incendiary rounds punched through aluminum skin and detonated inside the wing structure. More rounds struck the engine cowling. The fighter's propeller abruptly stopped, the engine seized by catastrophic damage. The aircraft rolled inverted and began a long spiral toward the Thai countryside below. Idness had opened fire at approximately 1,100 yards and achieved a kill before the fighter closed to 900 yards. The engagement had lasted less than 5 seconds from first trigger pull to enemy aircraft destroyed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth and content like this. Throughout the formation, similar engagements unfolded. Japanese fighters that had successfully attacked B-17s and B-24s over Burma and China discovered that the B-29 was different. The bomber's defensive fire began at ranges that seemed impossible. Tracers converged from multiple turrets, creating cones of fire that allowed no safe approach vector. Fighters that pressed attacks absorbed withering fire that shredded control surfaces, punctured fuel tanks, and killed pilots. The few that survived to gun range found their own weapons inadequate against the superfortress's altitude capability and speed. The mission to Bangkok resulted in 14 confirmed fighter kills and 9 probables, credited to B-29 gunners. 5 superfortresses suffered battle damage, but all returned to base. Not a single B-29 was lost to enemy fighters. The exchange ratio, 14 confirmed kills to 0 losses, stunned Air Force planners accustomed to accepting 6% losses per mission as inevitable. The GE Central Fire Control System had proven itself in the crucible of combat. Over the following months, as B-29 operations expanded from China bases to the Mariana Islands, combat data accumulated. Gunnery officers compiled reports, analyzed engagement ranges, calculated hit percentages. The statistics validated what crews already knew from experience. The computer-controlled defensive system worked, and it worked dramatically better than manual gunnery. Sergeant Idness, in a letter written decades after the war, described the system's performance with characteristic understatement. "The GE system proved very good," he wrote. "The computers would put in the lead and elevation needed to hit the target. I could get 75% hits at 1,000 yards while flying at 250 miles per hour. 75% hits at 1,000 yards against manually aimed guns that achieved perhaps 10% hits at 600 yards. The improvement was staggering. The effective range had increased by 67%. The hit rate had increased 7-fold. The combination created a defensive capability that fundamentally altered the tactical balance of air combat." Official combat reports confirmed Idness's experience. A report from General Echols, written in mid-1944, noted that during one mission, a gunner achieved 11.5% hits at 900 yards against a maneuvering target. The same gunner achieved 50.5% hits at 300 yards. The data suggested the system's effectiveness increased as range decreased, but remained useful far beyond the effective range of conventional defensive armament. Results indicated, Echols wrote, that the decision to continue with the GE equipment was well warranted. The B-29's combat record supported this assessment. Between June 1944 and August 1945, B-29s flew over 31,000 combat sorties against Japanese targets. Gunners claimed 914 aerial victories. 72 B-29s were lost to enemy fighters. The exchange ratio, nearly 13-1, was unprecedented for unescorted bombers operating in contested airspace. For comparison, B-17s over Europe, despite fighter escort for much of their missions, suffered approximately 1 loss for every 3 enemy fighters destroyed by defensive gunners. Specific engagements demonstrated the system's capability under extreme conditions. On January 27, 1945, a B-29 identified in mission reports as B-29, a Square 52, participated in a raid on Tokyo. During the mission, 2 Japanese fighters attempted ramming attacks, deliberately colliding with the superfortress in kamikaze-style assaults. Both fighters succeeded in striking the bomber, causing significant structural damage. But the B-29's gunners, using the Central Fire Control System, shot down 12 additional fighters during the running battle back to Saipan. The crippled bomber flew 1,500 miles on 3 engines, crash-landed at its home base, and was written off as beyond economical repair. All crewmen survived. The mission demonstrated both the punishment a B-29 could absorb and the devastating effectiveness of its defensive armament when properly employed. Another notable engagement occurred on June 1, 1945, when a B-29 nicknamed Peachy encountered heavy fighter opposition over Osaka. The aircraft's gunners engaged 79 separate fighter attacks during a single mission. They claimed 7 confirmed kills. Peachy returned to base with extensive damage but no crew casualties. The gunners credited the central fire control system with keeping attackers at distance, preventing close-range attacks that would have been catastrophic. The system's effectiveness created unexpected tactical opportunities. General Curtis LeMay, commanding 21st Bomber Command from the Marianas, recognized that B-29s didn't require the same level of fighter escort as earlier bombers. The superfortress's altitude capability, exceeding 30,000 feet, placed it beyond the effective ceiling of most Japanese fighters. Those few Japanese aircraft that could reach operational altitude faced computer-controlled defensive fire that made attacks prohibitively dangerous. LeMay famously stated that these big boys can take care of themselves, and began dispatching B-29s on missions that would have been suicide for B-17s or B-24s. The most dramatic tactical shift came in March 1945, when LeMay ordered B-29s to abandon high-altitude daylight bombing in favor of low-altitude night incendiary attacks. The new tactics had the superfortresses attacking at 5,000 to 8,000 feet, altitudes where Japanese fighters could easily intercept. But the raids occurred at night, when defensive gunnery became nearly impossible for manually aimed weapons. The B-29's computer system, functioning independently of light conditions, retained full effectiveness. Japanese night fighters that attempted intercepts discovered that the darkness provided no protection. The computer tracked them through the gun sight's reflector reticles, calculated intercept solutions, and directed fire with the same accuracy as daylight engagements. The firebombing campaign that destroyed 67 Japanese cities between March and August 1945 was enabled by the central fire control system. Without computer-controlled defensive armament, low-altitude night attacks would have resulted in catastrophic losses. With the GE system, B-29s flew more than 33,000 low-altitude sorties with acceptable loss rates. The strategic impact was decisive. By August 1945, Japan's urban industrial capacity had been effectively destroyed, making invasion less costly or perhaps unnecessary. Yet despite this success, despite the system's proven combat effectiveness, despite the lives saved and missions accomplished, the central fire control system was removed from the B-29s assigned to the war's most important missions. The irony was bitter and absolute. In late 1944, the Manhattan Project began modifying B-29s to carry atomic bombs. The modifications, designated Silverplate, involved extensive changes to the aircraft's structure and systems. The bomb bay was enlarged to accommodate the massive weapons. Fuel tanks were reconfigured to extend range, and the defensive armament was stripped out. The upper turrets, the lower turrets, the side guns, all removed. Only the tail turret remained, a token gesture toward self-defense. The official justification was weight. The atomic bombs, Little Boy and Fat Man, weighed nearly 10,000 pounds each. Every pound saved in defensive armament was a pound that could be devoted to fuel, extending range, and providing safety margins. The engineers calculated that removing the forward turrets, the computer systems, and the associated electrical infrastructure saved approximately £3,000. Those £3,000 translated to perhaps 200 additional miles of range, enough to ensure the Silverplate B-29s could reach their targets and return to base. But the decision reflected something deeper. The atomic missions would be flown at high altitude, above 30,000 feet, where Japanese fighters struggled to intercept. The bombers would approach individually, not in formation, making them difficult to detect and track. The missions would be executed with absolute surprise, giving Japanese defenses minimal time to respond. The planners believed, perhaps correctly, that stealth and surprise would provide better protection than guns. The logic was sound, but the symbolism was striking. The most expensive weapons system of the war, a $3 billion program that had revolutionized defensive gunnery, was deemed unnecessary for the most important bombing missions in history. The Enola Gay, which dropped the atomic bomb on Hiroshima on August 6, 1945, carried only tail guns. Bockscar, which bombed Nagasaki 3 days later, was similarly stripped. The aircraft that ended World War II did so without the defensive system that had enabled their entire operational campaign. The Central Fire Control System's legacy extended far beyond World War II. After the war, the B-29 continued serving through the Korean War, where the system again proved its worth. On December 18, 1972, nearly 3 decades after the system's combat debut, B-52 Stratofortresses flying Operation Linebacker, 2 over North Vietnam engaged MiG-21 interceptors. Staff, Sergeant Samuel Turner, operating a B-52's tail turret, shot down a MiG at 2,000 yards using a fire control system that traced its lineage directly to the GE equipment developed for the B-29. Turner became the first bomber tail gunner to shoot down an enemy aircraft since the Korean War. 6 days later, on December 24th, Airman Albert Moore shot down another MiG-21, this time engaging at 4,000 yards. Moore's kill represented the last time a bomber tail gunner destroyed an enemy aircraft with machine guns during wartime. The technology pioneered by GE engineers in the early 1940s influenced every subsequent bomber defense system. The integration of radar, the networking of weapons, the automation of fire control, all built on concepts first implemented in the B-29. Modern aircraft, from the B-52 Stratofortress to contemporary stealth bombers, employ descendants of the Central Fire Control System, though weapons have evolved from machine guns to electronic countermeasures and defensive missiles. The mass production of the GE computers, thousands of units manufactured between 1943 and 1945, represented the first large-scale deployment of electronic computing technology. The program demonstrated that complex analog computers could be manufactured reliably, maintained in field conditions, and operated by personnel with minimal technical training. The experience influenced post-war computer development, accelerating the transition from mechanical calculators to electronic systems. Engineers who worked on the B-29 fire control program went on to design early business computers, advancing the commercial computing industry that would transform global commerce in the 1950s and 60s. Perhaps most significantly, the program proved that automation could enhance human capability without replacing human judgment. The gunners remained in the loop, tracking targets and making engagement decisions. The computer simply amplified their effectiveness, handling calculations too complex and time-sensitive for human minds. This human-computer partnership became the model for subsequent weapons systems and, ultimately, for computing applications far beyond military use. The cost of the program, $3 billion, equivalent to approximately $52 billion in 2025 currency, made the B-29 the most expensive military program of World War II. The sum exceeded the cost of the Manhattan Project by more than 50%. Critics argued the money could have been better spent on proven systems, on additional B-17s or B-24s, on more fighters or tanks or ships. But the critics missed the essential point. The Pacific War demanded long-range strategic bombing capability. Conventional bombers couldn't reach Japan from available bases with sufficient bomb loads. Even if they could reach the targets, they couldn't survive the journey without fighter escort that didn't exist and couldn't be provided over the required distances. The B-29, enabled by its revolutionary defensive system, solved an impossible problem. It allowed America to strike the Japanese home islands before invasion became necessary. It enabled the blockade mining campaign that strangled Japan's maritime logistics. It made possible the firebombing campaign that destroyed Japan's industrial capacity. And it delivered the atomic weapons that ended the war. Every one of these missions depended on defensive armament that worked at ranges beyond what any previous bomber had achieved. Staff Sergeant Kenneth Idness, the farm boy from North Dakota who had been skeptical of the computer system during training, flew 35 combat missions as a B-29 Central Fire Control gunner. He survived the war, returned home, and spent decades working as an engineer for Boeing, the company that had built the aircraft he defended. In letters written late in his life, he reflected on the technology that had kept him alive through 35 missions over Japan. "We were all skeptical at first," Idness wrote. "The system seemed too complicated, too dependent on things that could break. But after the first combat mission, after we saw how it tracked targets and put bullets exactly where they needed to be, we became believers. The computer didn't miss. If you tracked smoothly and gave it good data, it would hit every time. I saw fighters at ranges where they thought they were safe, saw them take hits and go down before they understood they were in danger. The system gave us an advantage that Japanese pilots couldn't overcome. They were brave, skilled, determined, but they were fighting technology they couldn't match." The story of the B-29 Central Fire Control System isn't really about computers or guns or turrets. It's about the distance between impossible and done. In 1940, the idea of remote-controlled turrets directed by analog computers seemed like science fiction. The established contractor, Sperry, with decades of fire control experience, failed to deliver. The backup contractor, General Electric, with no aircraft gunnery experience, succeeded where experts had failed. They succeeded because they abandoned assumptions, because they built from first principles, because they tested relentlessly and fixed every failure. The engineers who made it work didn't know they were building the first mass-produced electronic computers. They didn't know they were creating the foundation for human-computer collaboration that would shape the next century. They knew they had 6 months to deliver a system that would protect bomber crews flying into the most heavily defended airspace in the world. They knew that failure meant American airmen would die by the hundreds, that missions would fail, that the war would be prolonged. That knowledge drove them through 18-hour days, through endless test failures, through redesigns that invalidated months of work. General Echols, watching the Sperry system fail in the frozen test range at Wright Field in March 1943, had made a decision that redirected $3 billion and mobilized thousands of engineers. He had bet on the backup plan, on the underdog, on the team nobody expected to win. His decision was vindicated in the skies over Japan, where B-29 gunners achieved hit rates 7 times better than conventional defensive armament, where engagement ranges extended 67% beyond previous capabilities, where the exchange ratio of enemy fighters destroyed to bombers lost exceeded 13-1. The gunners who flew combat missions in B-29s didn't understand the engineering behind the Central Fire Control System. They didn't need to understand the mathematics of differential equations or the electronics of servo amplifiers. They understood that when they tracked a target and squeezed the trigger, the computer would put bullets exactly where they needed to be. They understood that Japanese fighters that approached at ranges where they thought they were safe would suddenly find themselves absorbing accurate fire from multiple turrets. They understood that the system worked and that it kept them alive. 20,000 B-29 crewmen completed combat tours over Japan. Most survived, though many didn't. The defensive armament didn't make the bombers invincible. It simply changed the odds from impossible to survivable. That difference, between impossible and survivable, was everything. The Central Fire Control System transformed strategic bombing in the Pacific. It enabled missions that couldn't have been flown with conventional defensive armament. It saved lives that would have been lost to fighter attacks. It demonstrated that automation could enhance human capability in ways that seemed impossible before the technology existed. And it proved that sometimes, when experts fail and conventional wisdom offers no solution, the answer comes from unexpected sources, from engineers who didn't know it couldn't be done, from backup plans that became main efforts, from stubborn insistence that impossible simply meant nobody had solved it yet. In 1943, General Electric was told to build a system that conventional wisdom said couldn't work. 6 months later, they had proven the impossible was merely difficult. 2 years later, their system had helped win a war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.